Hello students, in this video lecture series we will discuss about one of the important phenomena called electromagnetic induction, EMI. Student, what is electromagnetic induction? So it's a introduction of current in the secondary coil due to change of magnetic field in the primary coil is called electromagnetic induction. Student, what we have studied in the chapter electricity, that the source of electric current is the voltage. There should be a voltage, then only the current flows. If there is no voltage, the current will not flow. Now, to create the voltage or the potential difference, we had a source called battery or the cell. But here, in this case of electromagnetic induction, the source of electric current is not the battery. The source of this current is not of electrostatic origin. It's something different. So in this case also voltage will be generated, but not because of chemical reaction, as in the case of a cell. So it's because of a magnetic field. So because of a change in magnetic field, we can develop a voltage, and because of that voltage, developed voltage, current flows. So this phenomena in which the voltage develops or the potential difference develops because of change in magnetic field and the current flows, this phenomena is called electromagnetic induction. So that's what we mean by this. Introduction of a current in the secondary coil due to change of magnetic field in the primary coil. Student, here we have this situation. We have a first coil. This is called a primary coil, where we have the source of a current. The battery is connected, and just adjacent to it we have another coil to which we have connected a galvanometer. So in this secondary coil, this coil is called secondary coil. So in this coil, you can say there is no source of a current which can make the current flow through this secondary coil. These two coils are placed very close to each other. If I plug the key in this primary coil, what happens? The current starts flowing through this coil. And you know, students, when the current flows through the coil, what happens? The magnetic field starts developing around this coil. So because of this magnetic field which develops around this coil, this magnetic field starts linking with this coil. And what the scientist found, that if the magnetic field which links with this, the magnetic field which is developed around this coil, if this magnetic field link with this, and that linked field starts changing, either increasing or decreasing, what happens? The current flows through it. How do you know the current flows through this coil? Because we have a galvanometer. The galvanometer will detect the flow of a current. We can see the galvanometer deflection. So galvanometer deflection means current flows. Now student, there was no source of a current in this secondary coil. There was no cell, there was no battery connected, but also the current started flowing. We saw the deflection of a galvanometer, indicating the flow of a current in the secondary coil. So what is the cause of this flow of a current? That's the linked magnetic field around this coils changes. When we plug the key, the current flows through it. Because of that current flowing, the magnetic field develops around this coil. That magnetic field linked with this, and that linked magnetic field changes. Changes means either increases or decreases. So that changing magnetic field makes the current flow through this coil, secondary coil. So this phenomena where the current change in the primary coil introduce a current in the secondary coil, this phenomena is called electromagnetic induction, EMI. This phenomena was first studied by Michael Faraday. Student, the current which flows through this coil, secondary coil, is given a name called induced current. Induced current. The current flows through this coil. The current which flows through this coil, secondary coil, is called induced current. This induced current has a direction, student. How do you know this induced current has a direction? What is the meaning of this induced current having a directions? Now suppose if the battery's poles, this positive pole and negative poles, if I reverse the battery's positive and negative poles And if I make the current flow, I can see the deflections in opposite directions. What does it mean? It means, see, suppose this is the battery's plus and this is the minus. If I plug the key, the current flows in one direction, and because of that, we can see the deflection in one directions. If I reverse this pole and if I plug the key and make the current flows in opposite direction, this way I can see the deflection in this galvanometer in the opposite direction, indicating the flow of a current in the reverse case, reverse direction. Student, one more time. Say, suppose I have a coil here. Say in this coil, this is the battery's plus and minus. So the current will flow in this direction. Because of this, galvanometer will deflect in one direction. Now say suppose I'll reverse the battery's pole. Let me just reverse this battery's pole like this. Now if I allow the current to flow, the current will flow in this direction. Because of this current flows direction, the galvanometer will show deflection opposite direction. Say suppose in this case the deflection was this side. Now in this case the deflection will be in this side. So reversing the direction of a deflection shows that this induced current has got a directions. So if this induced current has a directions, how do we determine the direction of the induced current? There is a rule called Fleming's left hand rule. Fleming's left hand rule. So using this Fleming's left hand rule, we can determine the direction of the induced current. So how do we use that rule, student? We studied about the Fleming's left hand rule. What does that rule says? Stretch the first three finger of your left hand. This is the center finger that indicates the current. This is the forefinger, indicates the field, and this thumb will give you the direction of the force. That was the Fleming's left hand rule. Now this rule says, that's the Fleming's right hand rule says, stretch the first three finger of your right hand mutually perpendicular. Now this is your right hand. Stretch this right hand, first three finger of right hand mutually perpendicular, such that first you have to adjust this thumb and this forefinger. Thumb in the direction of motion and this index finger or the forefinger in the direction of the field. Then the direction along which the central finger points will give you the direction of the induced current. See the difference between these two laws, student. This law, Fleming's left hand law, is used to determine the direction of the force. So what do we do in this case? We adjust these two fingers first and we find the orientations of this thumb. This gives us the direction of the force. So to determine the direction of the force, we use the Fleming's left hand rule. But this is a Fleming's right hand rule where we adjust this finger and this finger first. So when we adjust these two fingers, the direction along which this finger points gives you the direction of the induced current. So that's how we can use the Fleming's right hand rule to determine the direction of the induced current. Student, this EMI, that's the electromagnetic induction, is the working principle of electric generator and many more other electrical machines, which is based on this electromagnetic induction's principle. Student, I hope you understood today's lecture about the electromagnetic induction. So we'll discuss about another chapter in our next lecture. Thank you.